as the impulse response. So this is what we'll call as the impulse response. Some reason this.
It makes sense, Professor. But Professor, one thing that when the direct delta function, I mean, the input is direct delta, which is basically if you try to integrate over a system, it is 1. So the point is that how this delta t is coming to st, and then like triangular functions, you are saying that it will become. So those things, I mean, can you elaborate on that? Because somehow we are not able to relate that, yeah.
So your question is about the Dirac delta function itself, is it?
Yeah. So how it's getting transferred to HT within the LTI system? I mean that portion, yeah.
So the output is h of t. So an LTI system we don't know what is the internal mapping of the LTI system. So you give some input, it does some mapping. We don't know what is the mapping that is going on inside.
Okay.
So basically it is a function. It is a function of functions. A system, let's say there is some arbitrary system. We don't know what is that system. You feed in some arbitrary x of t. It produces some y of t. So basically what it takes is it takes a signal, transforms it to some other signal. So in that same fashion, it can take in a Dirac delta function, which is a signal, and transform it to some other signal. And the transformation that it produces is what we call as the impulse response. I don't know if that answers your question, or maybe if you rephrase your question more clearly, I can address it.
I mean, I can understand this, Professor, what you are saying, and I mean, I'll think over this again. I think I need some time to think over this. Yeah, thank you,
maybe,
Professor.
That's okay. So if you can tell me exactly which part is confusing, maybe I can elaborate a little more on that.
No, I was just thinking more focus on this LTI system, how it is getting taking the input and converting to the impulse response. So it is a multiplication of something or something like division or addition.
No.
Yeah.
There is no multiplication or addition when it comes to impulse response. The impulse response, it is basically like the characteristic of the function of the system. So you want to characterize the system by some parameter. Right? There is some parameter to the system, and that parameter is the impulse response. That's all.
Okay. Yeah.
Okay. So you feed in an impulse, whatever output you see is the characteristic or the parameter. Okay, you can think of that as a function of a function. The system is a function which will modify some function that is given to you.
Okay.
And that function is given to us as the input signal.
So on the similar line, the unit response functions been also derived on the similar line. Is it right, no, Professor?
Sorry?
The unit response function,
unit step response.
So, Professor, these are only two basic responses we consider so far in this signaling system, or
unit impulse response is all you need to understand. Everything else just follows directly from that.
Okay.
Unit impulse response is the fundamental parameter or characteristic of the system. That's it. Important. What is more important is the impulse response.
Yeah. Thank you, Professor.
Yeah, no problem. Any other questions? Jashmati, how does this usually work? Okay. Speaks it. Yeah, feel free to ask any questions that you guys have at this point of time.
I would like to ask one question.
Yeah, go ahead.
Yeah, hello, Professor. Myself Subhash, and first of all, thanks for spending your time. And so I would like to ask a general question. It's from week 5. So, I mean, I haven't understood the way you have connected the Dirac delta function to represent any arbitrary function, and the way you connected it to LTI systems.
Okay, so let's try and do that slide. So this is the one that you're referring to, right? Can you see the screen?
Yeah, but yeah. A little
This is
bit
the
more.
one.
Yeah,
For
where you have
this,
been explaining linearity is right. Yeah. I mean the next one itself. No, next one. Itself.
this is the first
Yeah,
slide.
please. Yeah.
All right. So basically, the idea is, let's say you have some arbitrary function, okay, some arbitrary function like this. So if it was discrete, then you can, let's say, I'll start with an example of a discrete case. So let us say I had a discrete function, something that looked like this. Okay. Now, if I had something discrete and then that goes on like this, let's say this is some 1, 2, 3, 4. Let's say that this is our discrete function x of 2. I can write this as 1 plus this function or this signal plus right. So basically what we have done here is, let's say that this is 1, this is half, 1 half. So we have taken this simple impulse, which is just unit value and 0 everywhere else. And we have just shifted that in time, scaled it and added it to get any signal that we want. Is this clear? So if it is discrete, it is easy to understand that we can take this impulse form and then just scale it and shift it in time and add it together to get any possible discrete sequence.
Yeah.
Right? This is exactly what we are doing, but in the continuous time here. Okay? So in the continuous time, when we have a signal which is continuous over time, in order to get the signal's value at any one point, what will we do? So we will say if the signal is x of t, I want to represent the value of the signal at only one point. Then I'll say t minus t. This represents the signal value at x of t naught. So if I have to plot this signal, how would I plot? I will say that at t naught, this is taking a value of x of t. So now this is basically sampling the signal at one particular point, and that point is t naught. Now, what if I sample this at several t naughts and add everything together? Okay. How would we do that? So let's sample at some t naught. So this is at one point. Now, what if I do this at multiple points? Okay. What if I sample at several t naughts? And how small is this t naught going to be? It is going to be arbitrarily small. So I'll start at 0, and the next point is arbitrarily small. Probably next point is 10 power minus 7, and then 2 times 10 power minus 7, and so on. So this 10 power minus 7, I can keep on reducing. I can have it arbitrarily close as close as I want. So you can sample at every possible point and then finally add together. So when this addition is going to be in a continuous domain, it becomes integral. Okay. So basically all this that we have written here is, this is just addition. Because it is continuous, this t naught is taking infinitesimally small value. We are going to say that this is an integral, it's not an addition. And because you're integrating, you're going to add a dt naught. And this t naught is from minus infinity to infinity. Basically, it's just taking each and every sample that is present inside this continuous signal and adding them together. That's the representation that we have here. So that is why we call this as the infinite sum of scaled Dirac deltas. You take Dirac delta, shift it to some time t naught, scale it with the value of the signal x of t at that time t naught, and then add with another scaled Dirac delta and another time. And what are the times at which you are sampling? All possible times from minus infinity to plus infinity. Putting everything together for a continuous value instead of summation, we have integration. That's all. Does it make sense?
Yeah.
Okay.
connected this with the linearity.
Okay, how does this connect with linearity? So if you have the signal value at, let's say, one particular point, let us say we have the signal's value at t naught. Now, if we are feeding this as the input to a linear system and we get some output, let's say the output of this particular input is some h t naught of t. Okay? I'm just naming it with some variable, that's all. So the output for input of this form is h t naught of t. If this is the output that I know for this signal, and if I feed another signal, let's say the other signal is xt of delta of t minus t1, and the corresponding output is h of t1 of t. Now, when I add these two, what would be the output? Because of linearity, the outputs will also get added up. Correct?
Yeah.
Now, for how many terms are we adding here? We are adding infinitely many terms. So this addition here is in fact an integration. And similarly, the addition here turns out to be an integration. But in this case, we cannot have integration over t naught, t1, multiple t's. So what gets simplified here is because of the time invariance. So what is time invariance? So the time invariance, so basically this is what we have. So we have x of t for a particular time instant. Now you keep adding it. So the addition, so this addition gets replaced with integration. All we are using is still linearity, that's all. So you can add two things, the output gets added up. Now if you add infinitely many things, the output still gets added up. Now because you are adding infinitely many things in continuous time, the addition becomes an integration. Now the question is, what happens to this output? So should I have an output which is at t naught, t1, t2, and so on? Or is there a better way of characterizing this loop? So this is where time invariance helps us. So if I know the output of an impulse at t minus t1, then the output of t minus t naught is simply a time shifted version of the previous output. That's what time invariance tells us. Okay? So in other words, if I know only the output of delta of t, let's say this produces an output of h of t, then what is the output of delta of t minus t naught? Because of time invariance, I can say this is the output. Okay, and because of linearity, I can say that the output of delta of t minus t naught is just h of t minus t naught scaled with x of t naught. We can say this because of linearity, right? If I multiply x of t with delta of t minus t naught, what do I actually get? This is what I get, an impulse which is scaled by this value, which means it is as good as having a scalar value, right? So if this is a scalar here, then the output also gets multiplied with the same scalar. So basically, this is all we are doing. We are saying that we'll exploit the property of time invariance and the property of linearity to simplify this input-output relationship. So you take an impulse, time shifted. When you time shifted, because of time invariance, the output also gets only time shifted, nothing else. And you scale it with some scalar. And that scalar turns out to be just one sample of your input signal. So the output also gets scaled by that scalar. Now you can change this scalar over time. If you change this scalar over time, how are you changing? Basically, you're changing by adding multiple time instances. Now, what if I want to add these two? This is the superposition property, right? So if you want to add these two, these get added up. Okay, so I don't have a good writing pad here, so this is going to look very ugly. So this also gets added up. Now here we have added only two signals. Now what if we are going to change this T0 and T1 infinitely from -50 to +infinity? This addition becomes an integral. And similarly here this becomes an integral. And the variable of integration is T0, T1 and all that, because that is the one that is changing. So effectively what we have here is something like this. Or x of tau times h of t minus tau theta. Does it make it clear, or is it still confusing?
Yeah, yes, sir. So here f of,
No,
f open square flower bracket, what is the notation? Is it just a
This is the
convolution?
LTI system. This is the LTI system. The F
Okay,
is basically the LTI system. So whatever is inside is the input. The LTI system here converts that input to this output.
yeah, we don't know what is happening, but we are just
Yeah, we don't know what is going on inside. Assume that it is a black box. All you know about the black box is that it is an LTI system.
Okay. So the reason we are using Dirac delta function is because it holds the linearity and time invariance.
Sorry, your voice was breaking. I didn't hear you. Can you repeat the question?
Okay, the reason we are using this Dirac delta function for this modeling.
So the reason why we are using Dirac delta function is because you can sample separate inputs at a particular point if I want to know what is the value of a continuous time signal. The only way to do that is by using Dirac delta. So I can just simply multiply the Dirac delta signal at that particular point and get the value. I can sample things only using Dirac delta. There is no other way to do that.
Thank you, Professor.
Okay.
So what if the input is also an impulse signal like direct delta? So direct delta signal will get convoluted with another direct delta function. Is it?
See, an impulse response is basically nothing but where an input is the Dirac delta function. So if the input is Dirac delta, the output is going to be the impulse response. Does that make sense?
Sorry, can you repeat that, please?
Okay. If the input of a system is a Dirac delta, then the output is the impulse response. You will get some function, you don't know what function, it can be any arbitrary signal. And that is the impulse response of the system.
And that's what we
Is that
term
your
as the
question?
characteristic. No, that's what we term as the characteristics of the function, how the function is
Correct.
defined, right? But
Yes, the characteristic of the system. Yeah.
but if means the xt signal, which is we are treating as the input, x tau, that is also a Dirac delta function.
Okay.
So the characteristic is derived using Dirac delta. So the convolution formula will be yt is equal to integration from -infinity to infinity, Dirac delta tau and Dirac delta of tau minus t d tau. Am I right?
Oh, no. So the convolution, what we're trying to say here is that, so your question is what happens when x itself is Dirac delta, right?
Yes, sir. Yeah.
That's what. So when x itself is a Dirac delta, then basically you can think of this as the impulse that you're feeding inside. So if that is the impulse you're feeding inside, then you get it sampled at only one particular point. So this entire integral is non-zero only at one particular point. For every other point, it is zero. So in this case, Dirac delta here operates like a sampling device. it samples at a particular time. So if your input itself is going to be Dirac delta, you can sample at only one particular point where it is non-zero, everywhere else it is zero. So for all practical purposes, after this integration also, you'll still get only a Dirac delta. Does that answer your question?
YT basically means the output that I will get from the LTI system, right?
Correct. So in this case, this is the output. And if your input is Dirac delta, then you have here Dirac delta.
Yeah.
Okay. So this gets mapped to the impulse response. We don't know what is the impulse response. Is that
That's
clear?
what we are terming as H tau T, right?
That's what we are terming as H of T, yes.
Okay.
Sir, could you take an example for better understanding? Sir, graphical representation and
Okay. See, the first thing in this particular slide, I have still not assumed any time invariance. So I have just explained here using linearity. So that's why there is a H tau here. Okay. And that H tau gets replaced with H of T or some H naught here once you assume this time invariance, because in this case, at any time, it is only shifted version of that. So what this says is, if, once again, maybe I can explain this with a discrete case so that things are easier, and then you can interpolate or extrapolate this to the continuous case. So let us say that there is a system, there is an LTI system. Okay. When the input of this LTI system is an impulse like this, a discrete impulse, basically this impulse is, let us say 1 at time t equal to 0. At every other point, it is just 0. This is my input. The corresponding output, let us say, is some arbitrary function that looks like this. This is just arbitrary. I'm drawing something 0, 1, 2. Let us say this is 2, this is 1, and this is some 1.5. Okay. So this is some output. So this is the LTI system. And this is the input. Let's call this input X of T. And let us call this output H of T. Now, somebody else gives me some other arbitrary function. Let us call that function Z of T. Now, it is an arbitrary discrete function. So what I can do is, let us say the function looks like this. Again, this is completely arbitrary. I've drawn something. So at -2, let us say it has value 1, and -1 it is 0, and at 0 it has 1, and at 1 it has, let us say, 1 again, and 0 everywhere else. So this is my Z of T. Now this Z of T, I can write it like X of T. So there is an impulse at -2 first. So I have to shift it to the left. So I can shift it to the left by this, and that is the negative direction. So minus X of T plus 2 captures this sample. Okay. And plus X of T captures this sample. And the final sample is now captured by another term, which is X of T minus 2. Is this clear? What we have done is we have taken an arbitrary signal Z of T, expressed that purely in terms of this discrete impulse. Okay.
Yes, sir.
yes, sir.
All right. So maybe if you want, you can have this amplitude as 2, and this will get scaled with 2. You can scale this amplitude. Now, if I want to find out what is the output of this Z of T, how will we find out the output? this is where we'll use the property of linear time invariance. So what is linearity? Linearity is telling us find the output of these things separately, and then you can add them together, scale and add those things together. Okay, that is what linearity tells us. So let's find the output separately for each of these terms. So what is the output for the first term, x of t plus 2? Now this is where we'll use invariance. The time invariance says that if you have the output at x of t, you can also find the output at x of t plus 2 just by shifting the output. So what is the corresponding shift in the output? So you just change the output to -2. So whatever was at 0, you move that to -2. Whatever was at 1, you move that to -1. Whatever at 2, you move that to 0, and everywhere else. So this is the output for t plus 2. Now, of course, you have to scale that by -1. So when you scale that by -1, the signs change. So the corresponding output would now be -2 at -2 and at -1. You have -1, and at 0 you have -1.5 and 0 everywhere else. So this is the output corresponding to this term. And then what is the output corresponding to x of t? That is h of t itself. And what is the output that corresponds to this term? So you basically shift. So let me redraw things. Now I want to draw it underneath this. So this is so messy. -2, -1. This is now you have the output for x of t, which is this. You have the output for x of t plus 2, which is this. Now we have to find the output for x of t minus 1. Okay. So let that be the one where you shift to the right. So basically you take this h of t, shift that to the right by 1, scale this entire thing by 2, this becomes 4, and you have 1, which is 2, and this 1.5 becomes 3. Now the final output is the sum of all these things. So the final output y of t. So I don't have the usual writing pad, so this is really tough to work with. So the final output is minus h of t plus 2 plus h of t plus 2h of t minus 1. So graphically, it is the sum of all these things. How does that look like? So at -2, there is this impulse that is coming here, right? What is that? That is -2. And at -1, you have once again this -1. And at 0, how do you compute the value of 0? It is the sum of all these impulses. So there is a 2 here. You have to add that with a -1.5 here. So at 0, what you will have here is 0.5. And at 1, once again find the sum. So here there is a 1 here, and there is another 1 here. So 4 plus 1, 5. So at 1 you will have 5. And at 2, what would you have here at 2? So you would compute this 1.5 added with this 2. So you'll have 3.5. And at 3, there is only 3 and nothing else. So there is 3 at this point and 0 everywhere else. So this is what you get when you convolve this input with this h of t. So essentially what we did, we just considered this as sum of multiple signals and then simply added them together. And this is equivalent to convolution. So if I had directly taken this input, which is of this form, and convolved with this impulse response, I would get this function. That is exactly what convolution does. And as you can clearly see, the length of the output is increased. It has increased by the amount of times by the length of the input plus the output, or input plus the impulse response. Is this more? Is this slightly better?
Sir?
Yes, sir.
Is this slightly better?
Sir?
Yeah.
So, is it possible to know the function of the system?
No, what function?
I mean, what the system does? I mean,
We don't know what the system does. So the system, like I said, is a black box. We don't know what is going on inside.
Yeah, so if we have more number of samples with its output, can we?
No, I used a discrete case here. I used a discrete case here only for explanation, but we are considering only continuous time systems. So I don't understand what you mean by samples.
No, sir. I mean, if we have more number of test cases like these signals, I mean, given this signal, we get this output. Given this signal, we get this output. Can we define the system at some point?
Okay. So it depends upon what are the test cases that you are giving. So what we know from the theory of signals and systems is that the best possible test case is the impulse.
Yeah.
If you give some other signal, we don't know if that will be sufficient. It may or may not be sufficient. If, for example, later we saw that you can give a unit step signal, and that may also be sufficient. Again, that will be sufficient for certain cases, not always. So there are certain test cases which will be useful. Example is impulse, unit step. So these two are what we'll see here in this course.
Yes. But
the best possible case is always the impulse.
Yes. And sir, in all these things, we generally use the impulse, right? And I mean the Paul-Dirac delta function.
Correct.
But this function itself is not a real function, right? I mean the practical function.
It is an approximation, correct? It is an approximation. It is not. You cannot get this in real life. No.
So how we do this analyze? I mean the computations in real life, in practical situations.
So one simple way is to use the unit step response. We can always get a unit step signal in real life, approximately.
Yes.
So you just turn on the system, and then from the time it is on, you can consider that the unit step has started. So that is an approximation that we often use in real life. So that is one way. You just feed it in a unit step and then see what is the output. So that is one way of finding out what is the response of a system. From there, you can also find the impulse response. Later, now we have started Fourier analysis. We'll see that there is a way just by looking at what is called as the frequency response, we can find out the impulse response indirectly from the frequency response. That
Yes.
we'll cover that when we study Fourier analysis completely.
Yes. And sir,
Yeah.
if we have two LTI systems,
Mhm.
and if we connect the output of one LTI system to as an input to the another,
Okay.
can we make a relation between these two LTI systems somehow, between the input of one and the output of the another?
So we can say the total system is the convolution of this is what I suppose you're referring to. That I'm highlighting here the slide. So what we can say at best is that if you replace these two boxes with just one box, then you can at best say that the impulse response of this one box, or the characteristic of this one combined box, is the convolution of the individual impulse response. That's all we can say. We cannot say anything more than this.
Yes, sir. And sir, when we give an input to a system, what happens inside of that system so that we get a particular output?
Okay, so think of a system as something which contains some kind of a memory. So when you feed in a signal, when you feed in a particular function or anything, what it will do is it will instantaneously see what is the current value, okay, and then scale it, either attenuate it or amplify it, and store it in the memory. The output that it produces is scaled sum of all the values that it has stored in the memory. So you can think of any LTI system, roughly speaking. Again, I'm going to take the discrete case for example. So you can think of a discrete LTI system as something like this, where you have multiple memory elements. Okay? So this is like delay 1, delay 2, delay 3, delay 4. So the output is something like this. It will take the current input, previous input from the memory, okay, so on. There's some amount of memory, we don't know how much. It will take all the values from the memory, scale it by some value, we don't know what it is. It will scale something and add everything together and produce an output. These are all added. So you can think of an LTI system something like this. Again, I'm giving you an example of discrete. You have to think of these things in continuous domain because that is what we are doing. In some sense, it has a memory. It stores things in the memory, and then from the memory, it picks up elements and then scales them. So this is the scaling factor. Whatever we have here, this is the scaling factor. So this will be like H0, H1, H2, H3, so on. So basically, these are the values of the impulse response. So it scales with these values and finally adds everything together and gives us the output. So you can extend this to a continuous time. So you can think of a system something like this.
So, sir, if we say it as a memory, is it something like a flip-flop or something?
A discrete LTI system you can probably model with an flip-flop, yes.
So
Not a continuous.
In case of
continuous time will be like a capacitor.
Okay. So
a capacitor can store your
ADC inside, or it's not possible?
See, no. So you are giving examples of the system. So these are all examples of an LTI system. Yes, an ADC can be an example of an LTI system.
Okay.
Again, not the entire ADC is not an LTI system. Certain parts of it is an LTI system. So a flip-flop for a discrete case, you can think of that as an LTI system. Yes, but in general, no.
Yeah. Yes.
For a continuous time, probably you can think of capacitors or inductors or a series or parallel connections of capacitors or inductors as LTI system because they have memory. You can store something in capacitor and you can discharge from it. So basically, it is the equivalent of continuous time memory.
Oh, yes.
Any other question?
Professor, one question. For the convolution, why we are reversing the one signal? Is it any other reason than, I mean, imposing like from the origin to the end? Any other reason other than this?
So I was explaining with this discrete time example, right?
Yeah.
So you can see what happens here. So the sample that came at the beginning, so the input first sample is -2, right?
Yeah.
That is what that needs to be added first. So when you flip the impulse response, what does it actually do? So if this is your impulse, when you feed in an impulse as the input, you get this exactly as the output. So the flipping is essentially to ensure that you add the corresponding time outputs. So as you can see here, what did we do? So we added up the signals that came at 0, exactly at 0, right? And something exactly at 1. So how can we ensure that in convolution? We are ensuring that you are adding all the outputs that came at time 0 to be added up at 0 is by doing this time reversal. If you don't do this time reversal, then you will not get this time synchronization.
Understood. Yeah.
Does that make sense?
Yeah.
Sir?
Yeah.
Sir, my question is related to the same system thing. So for taking the impulse response, we give the impulse as an input, right?
Correct.
So the impulse is just a momentary thing, right? Signal.
Correct. Correct.
So for a momentary signal, how it can give a this much, I mean, non-momentary signal as output?
So this is again whatever I said earlier. The system has memory, so you just give one input, but because it has memory, it keeps getting stored and then keeps giving output continuously. You think of a capacitor. You charge it once and then remove the battery, and you can continuously keep getting voltage across the capacitor till it completely discharges. So even after you take away the battery, why is it still giving you output? That is because it has memory.
Yes.
Like think of if you want it even simpler, you have a sequence of flip-flops. You just feed in one bit and then take off your input. Think of this as a linear shift register where this one bit keeps moving from one flip-flop to the next flip-flop to the next flip-flop at every clock cycle. You'll still keep getting an output, right? Like a counter.
Yeah, correct.
Yeah.
Okay. Yeah, sir. Good.
Professor, this limit for the integration, like suppose two signals are convoluting, then we are doing the manual calculation to plot it, the outcome. So can you briefly tell on that limit of integration?
What exactly do you mean limit of the integration?
I mean, for example, suppose a rectangular signal and an impulse response, but a triangular signal is given. Yeah. So it is getting convoluted. Then what limit I should integrate and then add up and to plot the outcome? Yeah.
Okay. So let us say that you have signal. Let's call this x of t. Okay. Some arbitrary signal. It exists from, let us say, minus t1 to plus t2. And there is another signal. Let's say this is h of t. It exists from, let's say, minus t3 plus t4. Now, if we are integrating this, okay, so the integration is minus infinity to infinity, x of tau, h of t minus tau. And it's up to you. You can integrate in any order. Doesn't really matter. So if we are doing this order, then the variable of integration is tau. Okay, and x is directly in the variable of integration, which means only in this interval x of tau is non-zero. In all other intervals, this is 0. Okay, so you are integrating over tau. So if you substitute any value of tau for which it is greater than t2, this term is going to be 0. So the entire product is 0. If it is less than minus t1, once again it is going to be 0. So you can change the limits to this. Okay, and it does not really matter what are the limits of h, because anyway t is going to run from minus infinity to plus infinity. So this term can be non-zero for any value of tau. Okay, if you are integrating it in this manner, where you have h of tau times x of t minus tau d tau, then your limits can be minus t3 to t4, because h of tau, because now the variable of integration is directly inside h, and that h of tau is non-zero only between minus t3 and t4. In this case, you can integrate it in this limits. Here, the limits of x does not really matter. Is it clear?
Yeah, and Professor, T1 minus T1 to T2, I mean, it can be further broken in the more what do you call interval while integrating.
Yeah, so if your signal is something like this, let's say this is some minus t5, t6, you can break this further down into two integrals. You can write this as minus t1 to t minus t5 plus t6 to t2. You can do this, right?
Yeah.
Okay.
Yeah, please. Thank you.
Any other questions? Yeah.
Sir, while doing this, the property of the signal being odd or even, does it have any significance?
Not really, because
of h of t.
See, if x of tau is even, h of t minus tau, we don't know what it will be, because you're shifting t.
Yeah, correct.
See, shift operation does not maintain symmetry.
Correct. Yeah.
Correct. So because we keep shifting here, there is no symmetry that is maintained. So because of which it does not have any effect of this on this integral.
Yeah, yes, sir.
Okay. Any other questions?
Sir, in one of the lectures, you did the analysis for a simple RC filter.
Right.
Can we do some same kind of analysis for RL? I mean,
Of course. Yeah.
I mean, if we can do it in this session, maybe that will help us revise through that particular lecture as well as improve our confidence in that kind of analysis for any network.
So see, you just replace C with L and then you will just get an integration. It will be the same thing. So nothing else was different. So I'm doing Fourier transform this time.
Yeah.
Okay, so the analysis of the RC circuit is going to be much simpler with Fourier series. So let's see that. So things will be much simpler when we study Fourier series and use that for the analysis of the RC circuit. So I'm doing this RC circuit analysis now just for example. It's going to be very complicated with convolution. So don't worry about extending that to RL or RLC and all those things. When we effectively use this analysis for circuit analysis, we'll never do all these things. We'll use only Fourier series and Fourier transform.
So that leads me to my second question, like Laplace transform and Fourier series or Fourier transforms are like techniques used for similar purpose. Is my understanding correct?
Correct.
And same goes for convolution.
Now, convolution is a little more general because there can be cases where Fourier transform and Laplace transform does not exist. Okay, so there'll be like those are very rare cases, really, really rare. But there are certain cases where both of these transforms do not exist. In that case, the only solution that we have is to convolve.
Okay, and between Laplace and Fourier, how should one choose for the purpose of analysis? Which one to?
Okay, so each of them have different use cases. Technically, Laplace transform is a little more general, meaning there are cases where if a Laplace transform exists, again, we'll see details of it. If it covers what is called as this origin, then Fourier transform will automatically exist. So that in most cases, Laplace transform will subsume Fourier transform. It's like a more general case of Fourier transform. And it makes more sense to use Laplace transform for real-life signals, for causal signals. Whereas Fourier transform could be used to analyze non-causal systems also. So when you are designing a system and you want to optimize it, let us say you don't worry about the causality. So if you are not worrying about the causality, it means that you are not really worried about how to implement it, but you just want to know what is the optimal system. In that case, you use Fourier transforms, because Fourier transforms can give you systems which are even non-causal. Whereas Laplace usually is applied only for causal systems. Okay? So if you are analyzing real-time systems, existing practical systems, then typically we stick to Laplace transforms. But if we want to know what is the optimal system, then we try to use Fourier transform.
Thank you.
And I'm talking only in the context of circuits. Of course, Fourier transforms comes into picture in a completely different context in many different fields. It comes in mechanical engineering, it comes in communication systems, it comes in control systems in many different ways. So I'm talking only in the context of circuits.
Sir?
Yeah.
So I understand why we go to frequency domain from the time domain, but somehow in midway sometimes I get confused the reason behind it. Would you give the details?
The only reason you always keep the eigenfunction reasoning in mind. The only reason that we go to frequency domain is because the phasors or the complex sinusoids, they are eigenfunctions. That's all. It makes our life simpler. You don't have to do the integration in convolution at all. If you feed in an eigenfunction, the output is a scaled eigenfunction. So there is no trouble doing this integration to directly get the eigenfunction as the output. That is the motivation, that is the primary motivation why we go to the frequency domain.
Okay,
in fact, in the discussion of the Fourier transforms, we will see that the moment you represent everything in the Fourier or the frequency domain, the input-output relationship simply becomes a multiplication. So if you know the frequency domain representation of the input and the frequency domain representation of the impulse response, the output is simply a product of these two. There is no integration. You just multiply pointwise and you're done.
Yes, sir. Okay.
Does that answer your question?
Yeah, yes, sir. Yes, definitely. And sir, if it's possible, could you also add some practical applications of the concepts which we learn in the lectures, so that it would be more enthusiastic?
So what I'm planning to do is, once I finish Laplace transform, I'm planning to do one case study. Probably I'll take a particular filter. I'm thinking of Butterworth filter, and we'll do a complete analysis of Butterworth filter using Fourier transforms and Laplace transforms. And once you're able to design a Butterworth filter with that, maybe you can design an audio equalizer and all those things. So wherever possible, I'll include some practical examples and applications.
Yeah, thank you, sir.
Professor, I think the question what I'm asking is may not be in the scope of this course, but I want to understand the power and energy of the signal. What is its significance for the application point of view? In the application point of view.
Okay, so the definition of energy technically is not what we physically refer to as energy. So it is more like if we have a vector, then we can define the length of a vector, distance of the vector from another vector. So is there an equivalent of that for a signal? And that equivalent is energy. And where this definition comes really handy is probably not in circuit analysis, but maybe in other domains. For example, if you are a telecommunication engineer, then this notion really helps to understand what happens to signals that you transmit when you represent baseband signals. Then what is the signal to noise ratio when you define them? In those scenarios, these definitions of energy will come into play. So this is more like, think of this as just defining the length of a vector. The energy of a signal is equivalent to the length of a vector, where the vector is the signal itself. And of course, if your signal is now a voltage signal or a current signal which is passing through unit resistance and all, then you have this interpretation. In certain cases, you can interpret this as the electrical energy across a device, but not always.
And for the power, Professor, the power?
Yeah, power is average energy, that's all. If you know energy, then power is just the average energy. So this is, for in terms of length, it is like the normalized length. So if you want to normalize the length, then how would you normalize?
Yeah, makes sense. Yeah. Thank you, Professor.
But sir, for signals, in case of signals, for signals having finite energy, the power is 0, right?
Correct.
So if we assume the vector length, I mean the signal length as energy, and the average length as power, it doesn't agree with each other.
So I'm not saying it's the average length, I'm saying it's a normalized length. So think of a space where you have vectors which have almost infinite length and vectors which have finite length. And if you want to normalize this and you want to say that I want to normalize this with respect to the largest vector in this case, then any finite length vector will become almost 0 in value when you normalize that with another vector which has really, really large length. Does that make sense?
Sorry, sir, I got disconnected. Could you please repeat one thing?
Okay, so think of it. So this is a space where you have a lot of vectors, where some vectors have finite length and there are other vectors which have infinite length. Now, essentially what you're trying to do is, in some sense, trying to normalize this with a number of vectors, kind of. Okay, it's a number of vectors in this space. So if you think of normalizing the length of the vector or the number of vectors in the space, the number of vectors is infinitely large. Okay.
Yeah, I see.
And if anything which has a finite length will automatically have 0 normalized length.
Okay.
It depends upon what is your normalization factor. Okay.
Okay, sir.
In this case, the normalization factor itself is tending to infinity.
Yes, sir. Okay. Yeah, yes, sir.
Any other questions?
Sir?
Yes.
My question is, if a system has a memory, then
Your voice is breaking. Your voice is breaking. Maybe you can type.
Yes, sir. Hello. Now
Yeah.
it's better, sir.
Yeah, much better. Go on.
Hello.
Yeah, it's better. Go on. I can hear you. Go on.
So, sir, my question was that if a system has a memory, then we can say it's always be causal.
No, not necessary. Just because system has memory doesn't necessarily mean it is causal. For example, let us say that there is a system whose impulse response looks like this. This is 0, this is 1, this is -1. Let us say there are impulses in all these three places. The system has memory, and it is also non-causal because it has non-zero values for the negative values.
And sir, in lecture you mentioned that if a signal means have some non-zero value for negative time, then it will be non-causal. What is the mean, sir? I didn't get.
Okay, so what does this mean when you convolve this impulse response with the input? So when you convolve the impulse response with the input, what do? You flip it, right? So whatever is on the left-hand side, that is corresponding to the negative values of time, come to the right-hand side. So that if it comes to the right-hand side, that it means that it is getting multiplied with the future values of the input. So for example, let us say this is your input. Okay. So this is my x of t. This is 0. And let us say my impulse response looks like this. Okay. 0, this is, let's say, -1. And now, if I try to find out what is the output of this system at 0, the output of this system at 0, let us say this point is -2. So this is not to the scale. Okay. So if I try to find out the output of the system for 0, what would be the corresponding output? So the impulse response says that at -1, there is an impulse, and at +1, there is another impulse. So till 0, I want to find out what is y of 0. Okay. Till 0, how much has been fed into the system? Only this portion has been fed into the system. This portion that is present here is not even seen by the system yet. But because of this impulse response, it says that there is an impulse at -1. What is the output? The output is at y of 0 is basically the sum of the signal at this point and at this point. So basically, it depends upon whatever was the value that is present after 0. So you have to add the signal's value at x of 1 and x of -1. Okay, and that is the output at y of 0. The y of 0's output is x of -1 plus x of 1. So this x of +1 is coming because of the impulse at the negative value of time. So this says that the output at 0 is actually depending upon the future's input. Output at time t equal to 0 second is depending upon the input at t is equal to 1 second, which is non-causal because you have not even seen this input yet. It is in the future. So you are saying my present output is going to depend upon my future input. And that is because of whatever is present here in this side. And that is why we say that if the impulse response has non-zero values for the negative values of time, then the output is going to be a non-causal output, and the system is a non-causal system. Is it clear?
Yes, sir. Clear.
Okay. Any other questions?
Sir?
Yeah.
So why we have this non-causality thing?
Okay, so like I said, the practical systems never are non-causal. Any practical system that you can construct is always going to be causal.
Yeah, yes.
But if you want to construct the optimal system, in fact, when we do Fourier analysis, we'll see an example. I'll work this out. Let's say we want to analyze an ideal low-pass filter. Okay? An ideal low-pass filter is something which has a cutoff frequency, and everything below that frequency it will allow, and everything above the frequency it will not allow. It is an ideal low-pass filter. That is the optimal low-pass filter that you can ever construct. But if you analyze that low-pass filter, it will turn out to be a non-causal system. So the best possible filters that you can construct are always non-causal.
The real low-pass filters.
The ideal low-pass filters, which do not exist, which are not practical, they are non-causal. So whatever we construct in real life, they're all causal systems. So technically, they are not ideal. What we construct in practice is never ideal.
Yeah, yes.
We get some approximations which are approximately close as possible to the idea. That's all we can do. But we can never reach the idea. But to know what is the best, what is the optimal, we need to know non-causal systems. Only then we can know what is the best and how far are we away from the best.
So only for our understanding and
Analysis.
okay.
Exactly. Yeah. Okay. Any other questions? You can also give me feedback about how the lecture is going. How was the quiz? And any general comments, feedback?
Yeah, lectures are very good, sir. And your way of teaching is very easy to understand.
Okay, thank you. Any particular thing that you guys want to change or modify in the lectures?
So maybe
So
inclusions. Yeah, go ahead.
One thing was you wanted some more examples of practical systems that I'll try and what were you saying?
Yeah. So more questions to work out maybe.
Okay.
And maybe some kind of subjective assignment, because what I have personally felt means in multiple choice questions, quite often the guesses work if you have a fair bit of understanding of the concepts. But how to arrive at an appropriate answer, that approach I might not be getting right. So
okay, so this is going to be very difficult to implement because the portal does not allow really subjective questions, and it becomes really tricky to evaluate subjective questions.
we have subjective assessments in our Maths 2 course, just to mention it here.
Okay, so I'll check with the portal team here if that is possible. Like Jashwanti said, she has already checked. So it may not be possible for this course. Maybe that's a different portal. I'll check anyway, and I'll see if we can add something like that if it is possible. But at this point, I cannot guarantee anyway with them.
That's fine, sir. But even in increasing number of questions that we can try out, or maybe mentioning which questions we can try out from the reference books, That will help.
That can be done. Yes.
Sir, activity question also.
Sorry. Sorry, can you say that again?
Sir, my opinion is we can get activity question for per lecture.
What do you mean by activity question?
So that's actually, again, maybe the way math course is structured. In that particular course, we have a set of questions after each lecture. We call them
okay.
Yes,
we
sir.
call them activity questions,
Oh, I see. Okay.
or
It's also
assessment
objective
questions.
only, sir. So if it's possible, it would be good.
Okay. All right. We'll try to incorporate that. Was there another
And
comment?
yeah, I must also appreciate the MATLAB inclusion of MATLAB part of the analysis, like means the way in order to explain the concepts. So certain means that thing certainly helps us in conceptual understanding, in getting a better clarity of those concepts. So I think as student we must also pick up MATLAB skills, if not now, later down the line. So more of that sort of things, or even some kind of assignments of that sort, probably not graded, but that will be much appreciated.
Sure. So that's good. So I'm glad that it helps. So I'm not sure how many people here are conversant with MATLAB. So I can give exercises in MATLAB to try out. Whoever is conversant with it, you can use MATLAB and then try to see if that helps. Okay. So that'll be good. Yeah.
They're just picking up skills
certainly
on
what
MATLAB, but this certainly helps. Like this subject provides us the concept and the use case to make use of MATLAB as a tool. So we will certainly appreciate getting guidance on this front as well.
Yeah. So I'll probably give some exercises in MATLAB, and whoever is conversant with MATLAB, you can try and solve those. And whoever is not, you can try it in other tool. You can try in Python or whatever is comfortable for you guys. You can try. So certainly simulating and seeing things visually helps a lot. So all of you should try that. Okay. Let me do one thing. I'll paste in this chat box Google Forms where you can give your feedback. So you can also share this with your friends who is not here, so that I'll get an idea of what is going on with you guys and what is that you're expecting, and if there is anything that needs to be done. I'll take a look at this and then I'll incorporate those in the lectures. Okay, anything else? Yeah.
So, sir, this kind of sessions with you, we will be having frequently, right? Or at least in future also, right?
I did not get the question, sorry.
No, sir, I mean, the interaction with you like this, can we expect in future also?
I'll try to attend as much as possible.
Yes, sir. It would be very good for us.
Sure.
We expect it.
Sure.
And thank you very much.
Sir?
Yes.
I have a feedback regarding the presentation in the lectures.
Sure.
In this live session, you have been working out in a big size, right? It would be nice even if in lectures, if you work it out in a bigger font. Like it's too tiny sometimes.
I see. Okay. I see. Okay. I'll try to.
Now in the live session, you did well. It was very clear.
Oh, I see. Because the live session, I felt it was quite messy.
No, messy
okay.
is fine. That's fine. We are okay with that. It's just sometimes if it's very tiny,
Okay. All right.
That's my
I can increase the font size. Okay, sure. Thanks.
Sir,
Yeah.
by the end of the course, like, can we expect something like an lecture where you tell where, I mean, in which future courses will be using what concept we have learned?
Okay, sure, I can do that. So you will use this probably in every other course. You will see Fourier transforms and convolutions going forward in every other course that you're going. Any circuit analysis, any control systems, signal process, digital signal processing. You will see this everywhere. I can probably give one short lecture on how this is going to be useful later. Yeah. But that is, I can do that if I first finish covering all the topics that I want to cover. That is upon the time I have.
Yeah, yes. So basically, this is going to be the sign of language in most of the courses in future.
Yeah, this is like if you study mathematical foundations, if you study how to differentiate and how to integrate, you're going to use that in every course. Right? That's how this is going to be.
Yeah, thank you.
Okay. Any other questions or comments?
Sir?
Yeah.
So after completion of this course, I mean this subject, so what are the things we can do? I mean, we are expected to know.
That depends upon what your interest is. So do you want to be an hardware engineer? Do you want to be a software engineer? Do you want to be an analog
No, I
system
mean,
engineer?
only the signals and systems. Yeah.
Oh, okay. Maybe I don't understand your question. So is your question that what are you supposed to
I mean,
know
can
by the
we
end of
build a system? Like, can we produce a signal?
Okay, so by the end of this course, you are supposed to know how to analyze a system. Okay, so this is not about creating or generating a system, but this is about analysis. This entire course is about system analysis and signal analysis.
Okay, yeah, yes.
Yeah.
Yeah, yes.
Okay, what is it? Okay. Okay, Bode plot is not part of the syllabus, so most likely I'll not cover it. But once I finish all the syllabus, then I can include these in an extra lecture. I mean, at the end, if I have time, I can talk about how this becomes applicable in other courses, and I can talk about Bode plot as well. Yeah, I can do that. Again, it depends upon if I have enough time once I finish covering the topics in syllabus first. Okay, do we have any other questions or comments? So what are you guys doing? How many of you are currently in your undergrad, meaning you are just doing your undergrad? How many of you are just doing how many of you are working? Maybe if you're working, you can just type W in the chat window. Rest of you just raise your hands. Okay, interesting. So I want to just understand what is your motivation to do this online BS? What are your expectations from doing this online BS program?
Professor, I am currently working. Hello.
Yeah.
So, Professor, currently I am working on EV, automotive sector in EV, and my work is to work on battery design and many electrical component and electronic circuit as well. But I don't have a formal, degree in electrical and electronics. I'm basically electromechanical engineer. So it is like mix of, yeah. So in order to gain conceptual background, I am doing this course to enhance my skill. Yeah. So that is main purpose.
Good. No, I really appreciate everyone's curiosity and your your intention to put in efforts to learn this. I'm very happy to see such a crowd.
Yeah. And Professor, I want to compliment your team as well, because I see the TAs and all the teams are putting a lot of efforts to train, teachers. So we thank to every teaching assistant and every faculty.
Yeah, please thank Jashwanti here. Jashwanti is the one who is the TA that puts in a lot of effort for the course.
Yeah.
I see.
Yeah, thanks to everyone.
Thank you very much for your efforts.
May I ask you one more question regarding concepts or maybe the application of this this subject itself? So
Yeah, go ahead.
So I see, I mean, I might be wrong, but in more of a deterministic kind of scenarios or systems where we have such analysis required, do you
Right.
see like random systems requiring this kind of analysis, or we have to do this kind of analysis for probabilistic models?
Very good question. So, in fact, I don't know if you have this course. There is something called as random processes. Do you have this in part of your syllabus in your entire course curriculum?
Not sure, sir. We don't have that insight.
Okay.
Means what we may come across down the line.
Okay.
I mean,
So,
there are many optionals. It might be one of them, but we don't. We yet not have.
in fact, whatever you're studying in signals and systems will be useful even when there is a random input. For example, let's say you have noise in your system. Always, any system that you have in real life will have noise. There is no way there is any system which does not have any noise. So there is always some additive noise in the systems that we have in real life. And this noise is always random. There is nothing deterministic about it. It is always random. The input is random, the output is random. Whenever you feed in noise, the noise of the input is random, the noise of the output is random. But the way the system processes this noise is deterministic. The characteristic of the system is deterministic, which means that the statistics of the noise gets processed in a deterministic way. The input output at a given point of time might be completely random, but the statistics like the mean and variance and their correlation, they are all processed in a deterministic fashion. So when you study this course, random process, and in that course, you will probably know how to characterize a random process. Like if the input is completely random, then how do you characterize it? You characterize it using something called as this correlation properties. There is something called as stationarity. Stationarity says that if the statistics remain constant over time, then you say that it is stationary. Then there is something which is deterministic even in a completely random process. And those are called the statistical properties. And the way the statistical properties gets modified is once again through whatever you study in signals and systems. Okay? So this becomes useful even when there are random signals.
Maybe more on the philosophical note. Next question is like, is future predictable? Like to some extent.
It depends on the system. Yes. There are systems in which future are predictable, but there are systems
Weather
in which it
forecasting.
isn't. Yeah, that's what. So there are some systems where if you observe enough data from the past, you can probably predict the future. So a system which has a very long memory ends up being mostly predictable.
So like the
And the
system
system
means
which
if
has a
I
very short
characterize
memory mostly is unpredictable.
so stock markets, how will that be modeled, analyzed?
Well, nobody knows that. If somebody knows how to model the stock market, by now they'll be a billionaire.
Yeah.
So yeah, there is no proper way to model. Certainly not a linear system. The behavior is not linear. If it is anything that is linear, we can model that usually completely in full deterministic fashion using whatever you study in signals and systems. So often the stock market is always a nonlinear system. So many systems that you want to model or you want to predict the future, they are often nonlinear systems. And that requires a totally different theory than what we are studying in signals and systems. Here, our assumption is things are well behaved. They're all linear. In fact, when you design amplifiers in electric circuits and electronic circuits, there is a linear regime, there is a nonlinear regime. We will force ourselves to operate in the linear regime because we know what is going on in the linear regime. We don't know how to analyze things in the nonlinear regime. So we'll force ourselves to work in the linear regime. So that's how electric circuits work. Any electronic circuit that you have, your phone, your laptop, everything has a nonlinear region, everything has a linear region. We'll always operate in the linear region because analysis is easier in the linear region. Things are deterministic and predictable. So if you want to predict things, try to operate in the linear region. Everything is very much deterministic there. And
So
the
can
moment something
we
goes,
enforce such kind of constraints on systems which are apparently non-linear?
all our systems are non-linear. Actually, they have certain regimes in which they are linear. There are certain regimes in which we have non-linearity. So, like I said, most electronic circuits we operate in the linear regime. So that's a restriction that we give. We force it to operate only in the linear regime.
Okay. Thank you.
Yes. Go ahead, Kilesh.
Okay, I would like to ask something.
Yeah, go ahead.
So some of us are doing this degree as standalone. So
Okay.
any advice from your end or?
Okay. So one thing that you guys probably be missing is probably not in signals and systems, but in other courses is the lab exposure. I think you come here on summers for the lab courses, but otherwise you might be missing the lab exposure. So I would strongly recommend you guys to get as much hands-on as possible when you're here or through the kits that you have, the electric circuit kits that you have, or learn some simulation tools like PSpice and MATLAB. Simulation tools are very, very useful when you don't have hands-on. So you can try out things on these simulation tools. So I would strongly recommend you guys to work out everything as much as possible in MATLAB or PSpice. PSpice for your other courses, for your circuits courses, and for courses like signals and systems and signal processing, use MATLAB. So the more hands-on you get, better is your understanding.
Yeah. So to learn MATLAB, you can use the free MATLAB resources.
Yeah, so go to MATLAB's website. They have an amazing documentation. You can just go to MATLAB's website and then use their documentation to learn MATLAB. They have examples, they have syntax, everything. So that's how I learned MATLAB. So yeah, you don't need a separate course for learning MATLAB.
Yeah.
Anything else?
Sir,
Yes.
the signals which we have learned so far, it also includes light, right?
Yeah, it can include anything. The signals can be anything. It can be light, it can be any electromagnetic radiation, it can be voltage, it can be current, it can be even force in a mechanical system. It can be anything. Anything that can be measured is a signal.
Yeah, yes, sir. Yeah. Because most of the times light is forgotten as a signal. Yeah, yes.
That's what I said. So signal is very, very general. Anything that you can measure and assign a number to is a signal. If you want to find the height of a group of people, find that is a discrete signal. Okay. Anything to which you can assign a number is a signal.
Okay.
So, if
Yes,
I'm
sir.
not wrong, basically signal is a way of representing something with respect to other, how it changes and all.
A signal is, I would say, a function. There is an independent variable and there is a function of that independent variable. So in our analysis in the signals and systems, the independent variable often turns out to be time or frequency.
Yeah.
And then we'll say that some particular phenomena, for example, voltage level attains this value at this time, or the system responds to a particular frequency with this much attenuation or amplification. So the most generic definition of a signal is that it is a function of an independent variable, a numerical function of an independent variable.
Thank you.
Sir?
Yes.
Is there any attribute for a signal like speed? Or is it a speed
Sorry,
of
your voice was breaking. Can you repeat the question?
No, sir. Is it safe to assume the speed of a signal is speed of light?
Okay, so this is a very vague question. I don't know what is meant by speed here. So, like I said, it depends upon what is your signal. If your signal is representing a voltage level or it is representing an electromagnetic radiation, then yes, you can say that the time there proceeds with the speed of light. But if I'm measuring, let's say, the position of a car at a time t, okay, that is my signal. The x coordinate of my car at some time t is my x of t. Let us say that is my signal. Then of course it is not going to move with the speed of light.
Yeah, so it depends on the situation which we analyze.
Correct. It depends upon what is that you are modeling as a signal.
Okay. Yeah, yes.
Any other questions? If there are no other questions or comments, we can. I'll wait till you drop. Okay. We'll end the session in the next 2 minutes if there are no other questions.
Thank you, sir. Thanks for spending your time, and we would expect some more sessions with you in future. Thank you.
Sure. Welcome.
Thank you, sir. Good night.
Good night.
Yeah, Professor, thank you. Good night.
Good night.
Thank you. Thank you very much, sir, for your time. Good night, sir. Thank you, ma'am.
Thank you, sir.
Good night, ma'am.
Good night.
Good night.
Thank you, sir. Thank you, ma'am. Good night, sir. Ma'am.
Right.